Hey, welcome to Weather Patterns 2.1. Now, if you notice already, this video is going to look a little different because I'm kind of playing with different formats. So we're going to see how this one goes. Remember how these videos are supposed to work. These videos that you see from myself and some of the other teachers are supposed to be walkthroughs of an Amplify lesson. So just like you'd be doing in class, it takes us through each lesson in every tab. So what I'm looking for you to do is to shrink this video, maybe pause it, send it to the side of your screen, open up another tab and have Amplify, and we can go step by step through this video. With that being said, let's go ahead and jump in to Weather Patterns 2.1. You know, just like every lesson so far in Amplify, 2.1 starts with a warm-up. Now, this warm-up is an extremely easy warm-up and very quick, so we're not even going to listen to the science song while we do it. Oh, don't worry, we'll get to the science song. So what I'd like you to do is go ahead and hit pause and go to tab 1 and go ahead and go through that question where you're deciding which best describes how the sun heats the air. Now, here's a clue. You're going to want to think back to our oceans, atmosphere, and climate video, or climate unit, and see what we learned about there. Well, let's talk about our science song for this unit, the water cycle song. Yeah, it gets really catchy and gets caught in your head, and that's kind of the idea. Well, I don't know about you, but I'm kind of sick of just watching me dance to the video. Yeah, and it's also kind of strange that I'm in my garage in front of a green screen dancing to this song. So instead of me just being the awkward one, I want you. I'm offering a challenge for you to create your own dance video for the water cycle song. Come up with some unique way, maybe TikTok or YouTube, or in the old days, Musical.ly, and you could do a lot of this with your phone. Whoa, and make your own video. But I'm offering you a fun challenge in this weird break to create your own dance song to this water cycle song. Without further ado, our weekly watch of the water cycle song.
The water cycle takes the water and moves it up and down and all around the earth. The water cycle takes the water and moves it up and down and all around the earth. The water cycle takes the water and moves it up and down and all around the earth. The water cycle takes the water and moves it up and down and all around the earth.
Evaporation comes when the heat from the sun warms up all the groundwater, then it turns to water vapor. Condensation takes over, it goes up to the clouds. Water vapor cools down and it changes to a liquid now. Precipitation happens when the drops get big. It falls like rain, snow, sleet, and hail upon my head. I know it's the water cycle happening again. Evaporation, condensation, precipitation.
The water cycle takes the water and moves it up and down and all around the earth. The water cycle takes the water and moves it up and down and all around the earth.
Evaporation comes when the heat from the sun warms up all the groundwater, then it turns to water vapor. Condensation takes over, it goes up to the clouds. Water vapor cools down and it changes to a liquid now. Precipitation happens when the drops get big. It falls like rain, snow, sleet, and hail upon my head. I know it's the water cycle happening again. Evaporation, condensation, precipitation.
The water cycle takes the water and moves it up and down and all around the earth. The water cycle takes the water and moves it up and down and all around the earth. Evaporation comes when the heat from the sun warms up all the groundwater, then it turns to water vapor. Condensation takes over, it goes up to the clouds. Water vapor cools down and it changes to a liquid now. Precipitation happens when the drops get big.
That was awesome. That was quite the dance right there. So again, I challenge you, create your own videos and you won't have to just watch me dance around. Though, it is kind of fun. So today, we're going to be exploring what determines how much an air parcel will cool down. How do we know how low that air temperature will? Now, if you think back to chapter 1, that's important because we learned that the more that an air parcel loses energy, so the more that an air parcel cools down, the more condensation that will occur. And the more condensation that occurs, the more liquid rain. And so we were looking at in our question in chapter 1 about what's happening in Gale Town. Why are they having such large storms? So today we're going to answer that question. Well, what determines how much an air parcel will lose energy or cool down? So let's go ahead and take a look at the data for Gale Town. You can see here that Amplify has provided us with 4 different storms to look at and compare. We have Storm 1, which occurred before the dam was built, so before the lake was created. And Storm 2, 3, and 4, which are all after. Now, ideally, we would love to have more data than just 4 data points. I mean, that's not a lot. Maybe there's a lot of things happening here that we're just missing. But we can use these 4 data points to get an idea of what's happening in Gale Town. So let's pause this video for just a little bit. I want you to go ahead and look at the data to tell us what's going on in Gale Town. How did the dam affect the storm strength? Go ahead and pause the video right now. Well, I hope you notice that, yeah, the storms got stronger after the dam was built. Storms 2, 3, and 4 are larger than Storm 1. But there's something else happening here. It isn't just the dam that's affecting it. If you look, the storms are getting stronger. The further away we get from the dam being constructed, that was between Storm 1 and Storm 2, the stronger the storms are. Look at Storm 2 is stronger than Storm 1, but Storm 3 is stronger than Storm 2. And Storm 4 is even stronger than Storm 3 and Storm 2. What's happening that's making these storms stronger and stronger and stronger? Well, in chapter 2, that's what we are exploring. So let's go ahead and get out our science journal and let's add our chapter 2 question. So our chapter 2 question is, why is the amount of rain in Gale Town different from storm to storm? Why are we getting more rain further we go from building the dam? Why isn't it just always the same amount of rain? Well, now Gale Town is a made-up place by Amplify, but we can think of our own cases here in Oregon, in Sandy and Boring area in Welch's. Why do we have some storms that dump a lot of rain on us and snow, but when we have other storms, it might just be a drizzle? Why do we have different amounts of rain in different storms? So, in chapter 2, for the next couple weeks, we're going to be exploring why there's different amounts of rain in the storms. So, we're going to continue to explore this today by jumping into the sim. So let's go ahead and open up tab 2 and let's jump into the sim. So let's jump into tab 2 and let's take a look at it. We're going to start over here on page 1 of tab 2. You can see in tab 2, Amplify wants us to use the sim. We're going to be trying to figure out our question of the day: what causes an air parcel to lose more energy and to cool down further? So we're going to start off by launching our sim. So go ahead and click that and open up your sim. It'll pop up in another tab. Now, if you look really close there at step 1, it says we need to go to regional weather mode 1. So that means we have to click the menu and go to regional weather mode 1. And it does look different, right? This is not the sim that you just saw. You can see we can change the amount of sunlight to the surface, and we can change the amount of surface water. So today, what we are going to do is we are going to run 3 different tests trying to make different temperatures of air parcels. And so I'm going to do the first one with you. You can write down the data as we do it. And then you're going to do test 2 and test 3 on your own. So let's go ahead and try test 1. Now, if you go back to your data table down here, you can see test 1, we need to make a hot air parcel. We need to make the air parcel really, really warm. So to do that, if we think back to oceans, atmosphere, and climate, we learned that the more energy that is absorbed by the surface from the sun, the warmer it's going to get. And so let's go ahead and make the sunlight to the surface as big as possible. And you can see that arrow got really large. We're not going to do anything today with surface water. We're just going to change sunlight to the surface. So we've got a lot of sunlight. It's going to be absorbed by the surface. Let's go ahead and run that sim. And there you can see the energy is coming from the sun. That sunlight's being absorbed by the ground and by the water, and it's then being transferred back to the air. You can see our air parcel temperature is going up. It's 40 degrees Celsius. And there we have our cloud building. You can see that arrow showing energy is coming out, making condensation, and rainfall is coming out of our cloud. So we've had lots of condensation. And we can also notice it reached pretty high up into the air. So now that we've run this sim, we need to go to analyze. And there we have all the data that comes with our sim. Our air parcel started at 40 degrees Celsius. We ended at negative 35 degrees Celsius. That's pretty cold. And that means we lost 75 degrees Celsius of energy. That's a lot. In fact, you look right here, that's 153 megajoules. Now, if you remember in chapter 1, the more energy going out, the more condensation. So take a look at this. We have had a ton of condensation and rainfall, made them more of a moderate. So let's go ahead and take this information and let's put it into our data table. So our hot air parcel, the surrounding air was 15 degrees Celsius. The starting air parcel temperature was 40 degrees Celsius. So remember, we're going to go ahead and put this in 40 degrees Celsius. And we reached a height, we look up here, of 7.5 kilometers into the air. That's pretty high, 7.5 kilometers. Now, I just did that one for test 1. You are going to do test 2 and test 3 by changing the amount of sunlight, and then you're going to answer this question back here that says, look back in the table at the starting temperature of each air parcel and the height of each air parcel. What patterns do you notice? Remember, science is all about patterns. So go ahead and do test 2 and test 3 and answer the question looking for a pattern that you notice. So now that you've completed page 1 and we saw how air temperature changes with the amount of sunlight, I want us to go to page 2. In page 2, you are again going to use regional weather mode 1. But this time it's going to be a little bit more up to you. So you're going to jump into the sim, and there it is right there. We're going to be using regional weather mode 1. So if you're not already there for some reason, remember it's always under your menu, regional weather mode 1. You are going to create an air parcel. That means you are going to change this right here. And it's totally up to you. You could be creative. If you want to put it at a 1, you can do that. If you want to put it at a 5, you could do that. Anywhere in between, you're creating your own air parcel. I'm just going to pick a 4 because why not? And I'm going to run to see what happens to my air parcel when I have a level 4 of sunlight coming in. So you can see energy is being transferred from the surface to my air parcel. It reached 35 degrees Celsius. It's rising up. Condensation is creating a cloud. Eventually it's going to rain out. Some of that energy is being transferred out into the surrounding air. And you can notice I reached 6.5 kilometers in the air and I'm at negative 30 degrees Celsius. So I'm going to come over here and analyze, and I make sure I have all that data out there. Now, once I have that data, I do have a question that it wants me to answer. If I go back to tab 2, it wants us to see, what do you notice about the temperature of the surrounding air at different heights? So what happens to the air temperature as you go up into the troposphere? So go ahead and answer that question and jump back into the video when you're finished with that. So in working with the sim, what factor did you change to create different temperatures of air parcels? Well, if you think back to Ocean's Atmosphere and Climate, that unit, we saw that sunlight doesn't directly warm up the air. Instead, that light travels through our atmosphere, is absorbed by the surface, either the land or the ocean or water, and is then transformed into thermal energy, which then is transferred to the air. So, in the sim, what you saw was the amount of sunlight changed the air parcel temperature. More sunlight meant warmer air, at least near the surface, and then that air could go up. So you saw in the sim, the more sunlight, the warmer the air is, the air parcel. So that leads us to our vocabulary word, the troposphere. We're going to define troposphere as the lowest layer of the atmosphere. It's the layer of the atmosphere that we live and breathe in it. It also contains almost all the weather, and a rule of thumb is that it reaches from sea level to about 70,000 feet. So, in your science journals, please write troposphere and the definition. In addition to our vocabulary word, we also have key concept 5. Key concept 5 goes back to the troposphere and what you just saw in the sim. We have that the troposphere is the warmest at the surface and coldest at the highest. So the further you go up in the troposphere, the colder it gets. Now, that makes sense. Because if you think about it, if the sunlight is warming, going through and being absorbed by the surface, and that surface is transferring that energy to the atmosphere, the part of the atmosphere that's right next to the surface is going to have the most energy. Think of it like a pot on a stove. The part of the pot that's touching the stove is the hottest because it's right near where that energy is being transferred. Well, the same thing goes for our troposphere. Since the energy is being transferred from the surface to the atmosphere, the part of the troposphere that's the closest to the surface is going to be the warmest. And the part that's furthest away from that surface is going to be colder. So, the troposphere is warmest at the bottom and coldest at the top. The further up you go, the colder it gets. Now, we can also think about that. In Sandy, right, my house is about 1,000 feet. If I go up to government camp, which is around 3,000 feet, give or take a couple hundred feet around that, you would notice that it gets quite a bit colder. It's very often to have snow at government camp and just rain here in Sandy. So that is because the higher up you go in the atmosphere, the colder it gets. Now we're going to take that key concept and we're going to apply it. So I'm going to jump into the lab, aka the kitchen, and we're going to see how this actually can be playing out with an air parcel. Hi, welcome to the lab. What do we call this room actually?
The kitchen.
It's the kitchen, but we're going to call it the lab for this experiment today.
Well, my dad can't go at work without the coronavirus.
You're right. So instead of for the coronavirus, we're doing science in our house, aren't we?
Yeah.
It's pretty awesome.
With my best dad.
Ah, thanks, Avery. Well, let's look at this week's experiment. This week, we are looking at warm air and what happens with warm air. Does it sink or rise?
What?
Yeah, it rises. Hot air rises, and we're going to do an experiment today to prove it.
Make our own hot air balloon.
We did. We made our own hot air balloon. You're right. Well, just wait. Yeah, hold on to that part. Yeah.
With a blow dryer.
With the blow dryer. So here's what Avery and I did yesterday. We took tissue paper, like you'd get from a present. Yep. We cut it out, and we glued it together to make our own hot air balloon. Yeah, and so we are going to fill it with hot air from a hairdryer, right? Avery's going to hold it, and
Why up there?
Yeah, and what do you think is going to happen when I let go of this?
Float.
You think it's going to float up?
Yep.
Well, we're going to try it.
Or the float down already.
It might. We'll see what happens, right? We don't know. Okay, so I want you to hold this.
Okay.
Remember? Nope, we're going to do hot first.
Hot. hot.
Okay, so we're gonna sit there. You hold it straight up. So we're going to hold it up. 2 hands. Put the other hand on it. And there we go. So let's fill our hot air balloon up. So we're going to take a little bit to fill it up with hot air. We want it not just to be the air dryer that's blowing it up, but we want the hot air to be the actual thing. Good job keeping it perfectly still, Avery. I like it. So we are filling this hot air balloon up with as much hot air as we possibly can get in there. Right. So while we're doing it, we'll fast forward this part just so you can see it. We'll go in fast motion here in a second. Okay, you ready?
Yeah.
Okay, go ahead and take the hair dryer out. Oh, we don't want to push it. Wow, good job. Let's turn it off. Now, you saw it float up. Now, I know some of you at home are probably thinking, well, maybe it's just a hair dryer because the hair dryer doesn't blow it out. So we're going to do it one more time. Yeah. But this time, instead of it being hot, what are we going to do it to?
Cold.
Cold. Yeah, we're going to do it cold. We're going to see if there's a difference. Are you ready?
Yeah.
Same thing again. Let's hold it. Nope, you don't have to push it in. Just hold it. Hold it up. It's filled with air, not as hot. Oh, yeah, we aimed it down. You need to hold it still. We'll do it one more time. Hold it still. Quick. You can stand up here. There. Hold it still. Hold it right there. One more time.
We're hot.
Nope, we're cold. So don't move the hair dryer there, Avery.
Okay.
Keep it still. You ready?
Okay, Stephen, Dad.
There, welcome. Hey, great job. So you can see what happened when we had hot air in our balloon. It floated up, and the cold air, not so much. So let's think of the camera. So when we do an experiment, hot air, what is hot? If we have a bunch of hot air, what would happen to it?
Float
up. It float up.
To our roof, back down to our heads.
It did. So I want you guys to think about that when you think of weather, about what hot air is going to do. Awesome. Back to your video.
Back to your video. And remember, subscribe, you like all your videos.
Well, the lab didn't quite work like I had hoped, right? The balloon didn't fly up in the sky. But you could see that because of the warmer air, it stayed up longer than when it had cold air. That leads us to key concept number 6. If an air parcel is warmer than the surrounding air, it will rise. Now you might have heard warm air rises. Well, yeah, actually warm air is less dense than the surrounding air, and so it actually floats up. So, key concept 6. If an air parcel is warmer than the surrounding air, it rises. Warm air is going to rise up. So let's make sure we put key concept 6 into your science journal. So with key concept 5, key concept 6, we can answer the question, what determines how much an air parcel will cool? You see, we learned in oceans, atmosphere, and climate that the sun warms up the surface. Actually, the sunlight is absorbed by the surface, and that energy is transferred to the air from the surface, the land and the water. That energy will then be transferred to the air and warm up an air parcel. So, the more sunlight that strikes the surface, the warmer an air parcel will. Well, we also saw that a warmer air parcel will rise up into the air. The warmer an air parcel is, the higher it will go up. And we also saw that the troposphere is colder the higher you go up. So, the warmer an air parcel is, the higher it will go up, the more energy will transfer to the troposphere, and the more it will cool down. So, what I want you to do is I want you to play all of this out and go ahead and jump to tab 4, your homework. So go ahead and at the end of our lesson, go to tab 4, your homework. Now, before you jump off yet, I do want to kind of go over how this video works. Remember, if I talk too fast or you miss something or you just want more information, remember, you can always hit pause or rewatch something or go back. You're more than welcome to reach out to myself or Mrs. Rock or Mr. Wallace to get more information. And you can also try it again. Remember, sciences can be hard. And sometimes it takes a little bit before an idea kind of gets stuck and can grow inside your mind. But always remember, even though things might be difficult, to keep moving forward.